In electrical systems, a multi-wire branch circuit is a circuit that consists of two or more ungrounded conductors having a voltage between them, and a grounded conductor having equal voltage between it and each ungrounded conductor of the circuit, and that is connected to the neutral or grounded conductor of the system. A common application involves sharing a single neutral conductor among multiple hot conductors originating from different phases of a three-phase power system. The advantage of this configuration is that it can reduce the number of conductors required, potentially lowering material costs and simplifying installation. However, the proper application of multi-wire branch circuits requires careful consideration of the National Electrical Code, or NEC, regulations and potential current imbalances. According to the NEC, a neutral conductor in a multi-wire branch circuit can only serve a single dwelling unit. This means that in residential applications, multi-wire branch circuits can be used to supply multiple outlets of fixtures within the same house or apartment, but they cannot extend to other dwelling units. This restriction is in place to prevent potential hazards associated with shared neutral conductors between separate residences. When determining the ampacity of conductors in a raceway or cable, the NEC requires that all current-carrying conductors be counted. This includes the ungrounded, or hot conductors and any neutral conductors that carry significant current. The number of current-carrying conductors affects the allowable ampacity of the conductors due to heat dissipation considerations. As the number of current-carrying conductors increases within a raceway or cable, the heat generated by these conductors can become trapped, leading to elevated temperatures. To prevent overheating and potential insulation damage, the NEC provides ampacity adjustment factors that must be applied when there are more than 3 current-carrying conductors in a raceway or cable. These adjustment factors reduce the allowable ampacity of the conductors, ensuring that they operate within their temperature ratings. In a balanced three-phase system, the neutral conductor should ideally carry little to no current. This is because the currents in the 3 hot conductors should sum to 0 in the neutral. However, in real-world applications, loads are often unbalanced, meaning that the currents in the 3 phases are not equal. When loads are unbalanced, the neutral conductor will carry the difference between the currents in the 3 phases. The NEC requires that the neutral conductor in a multi-wire branch circuit be sized to carry the maximum possible unbalanced load. This ensures that the neutral conductor is capable of safely handling the current under all operating conditions. To calculate the maximum unbalanced load, one must consider the types of loads being served and their potential for imbalance. For example, if the circuit serves primarily lighting loads, the unbalanced load may be relatively small. However, if the circuit serves a mix of lighting, receptacle outlets, and appliances, the potential for unbalanced load may be significantly higher. In applications where the neutral conductor is expected to carry a significant amount of current, it may be necessary to upsize the neutral conductor to ensure that it has sufficient ampacity. This is particularly important in situations where the loads are highly unbalanced or where there is a potential for harmonic currents. Harmonic currents are non-sinusoidal currents that can be generated by electronic devices such as computers, electronic ballasts, and variable frequency drives, or VFDs. These harmonic currents can cause increased heating in the neutral conductor, potentially leading to overheating and failure. To mitigate the effects of harmonic currents, the NEC requires that the neutral conductor be sized to carry the maximum harmonic current load. In some cases, this may require using a neutral conductor that is larger than the ungrounded conductors. When designing multi-wire branch circuits, it is important to consider the potential for voltage drop. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, conductors should be sized appropriately and the length of the circuit should be kept as short as possible. The NEC provides guidance on voltage drop calculations and recommends that voltage drop be limited to no more than 3% for branch circuits and 5% for feeders. Another important consideration when working with multi-wire branch circuits is the potential for open neutral conditions. An open neutral occurs when the neutral conductor is disconnected or broken, which can result in dangerous voltage imbalances on the circuit. In an open neutral condition, the voltage on one leg of the circuit may rise significantly above the normal voltage, while the voltage on the other leg may drop significantly below the normal voltage. This can cause damage to equipment and pose a shock hazard to personnel. To prevent open neutral conditions, it is important to ensure that all connections are tight and secure, and that the neutral conductor is properly protected from physical damage. Additionally, ground fault circuit interrupters, or GFCIs, can be used to provide additional protection against shock hazards in the event of an open neutral. The NEC provides specific requirements for the installation and wiring of multi-wire branch circuits. These requirements cover topics such as conductor identification, overcurrent protection, and grounding. It is important to carefully review and comply with these requirements to ensure that the circuit is installed safely and correctly. One key requirement is that the ungrounded conductors of a multi-wire branch circuit must originate from the same panel board. This ensures that the voltages between the ungrounded conductors are properly phased and that the neutral conductor is properly grounded. Another requirement is that the circuit breaker or fuses for the ungrounded conductors must be rated for the maximum current that the circuit is expected to carry. This protects the conductors from overcurrent and prevents potential fire hazards. The NEC also requires that the neutral conductor be connected to the neutral busbar in the panel board. This provides a low impedance path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse in the event of a ground fault. When installing multi-wire branch circuits, it is important to use properly rated and listed components. This includes conductors, connectors, circuit breakers, and panel boards. Using substandard or counterfeit components can compromise the safety and reliability of the circuit. It is also important to follow the manufacturer's instructions for installation or maintenance. Improper installation or maintenance can void the warranty and create potential safety hazards. In addition to the NEC requirements, there may be local codes or regulations that apply to multi-wire branch circuits. It is important to check with the local electrical inspector or building department to ensure that the installation complies with all applicable requirements. Proper planning and design are essential for ensuring the safe and reliable operation of multi-wire branch circuits. By carefully considering the NEC requirements, potential current imbalances, voltage drop, and other factors, it is possible to create a circuit that meets the needs of the application while minimizing the risk of electrical hazards. In summary, firstly, multi-wire branch circuits can be a cost-effective and efficient way to supply power to multiple loads. Secondly, the NEC places specific restrictions on the use of shared neutrals, particularly in residential applications. Thirdly, when determining conductor ampacity, the neutral conductor must be counted as a current-carrying conductor if it carries significant current. Fourthly, unbalanced loads can cause significant current to flow in the neutral conductor, requiring that it be sized appropriately. Fifthly, harmonic currents can also increase the current in the neutral conductor, potentially requiring that it be upsized. Sixthly, voltage drop should be considered when designing multi-wire branch circuits to ensure that equipment operates efficiently. Seventhly, open neutral conditions can create dangerous voltage imbalances and should be prevented through proper installation and maintenance. Eighthly, the NEC provides detailed requirements for the installation and wiring of multi-wire branch circuits, which must be followed to ensure safety and compliance. And ninthly, it is important to use properly rated and listed components and to follow the manufacturer's instructions for installation and maintenance.